Okay, let me switch back to Notion. All right, so, and if you're not necessarily interested in the science of water, you can also research things like how water may impact the economy. So you can do, instead of doing like water crisis, like US water crisis, you can Google Scholar search US water crisis and economy. And now you're getting articles that's correlating the water crisis to how that might affect the economy, whether US or the world. So there's a lot of different things you can do with that. And for extra credit, if you want to share with me any cool articles with a little bit of blurb of what you learned about it, I'm happy to read over and have that discussion with you. Okay. So now on to the lesson. So today I will introduce how all of this works chemically. So this being water, why water is so important, how it interacts with the environment around it, and really unique properties of water. So my goal is to help you visualize what's going on so we know what a water molecule looks like, H2O, but what exactly is going on between the interactions of H2O and salts, or H2O and oils, fats. Okay. So water is the most vital natural resource for life. At least that's true for here on Earth. And that's why when you hear about scientists that are exploring life in other places, the first sign that they look for is water. So water is the first potential sign um, of of life. And one thing that I want to point out is that's true for Earth. And we aren't so sure if that's true for other places. And that's just because the physical properties of other planets are much different. The pressures, the gases, um, the way things interact may not be extremely relevant to what we know and how we learn science. Um, so it'll be interesting to see in the next 20, 30 years how that develops. I still do believe that water is extremely necessary, but we will see how true that is in upcoming years. All right, so let's take a look at this water molecule. So in the last lecture, we described H2O and how it has this charge separation. You have a partial negative and partial positive charge, but we really didn't get into the physical properties. So this isn't anything that you have to learn. I just want to share this with you for now. So this partial negative and partial positive, if you remember, has to do with the sharing of electrons. So these are considered covalent bonds. Covalent bonds are between two non-metals. So you have oxygen and hydrogen, non-metals. And between these two elements are two electrons. And these electrons are being shared between the oxygen and the hydrogen. That's what makes this bond a covalent bond. And that is a intramolecular bond, intra meaning inside. And that's different than hydrogen bonds, which are intermolecular bonds. So the way that I remember this is inter is similar to interstate. So interstate highways are highways that connect two different states. Intrastate or intrastructure are structures or highways that are inside of a body, inside of a state. So intramolecular covalent bonds, intermolecular hydrogen bonds between two individual atoms. And first thing you notice is there are three elements, but in this molecule, you would expect for it to be a straight line. The reason why it's not is because there are two lone pairs of electrons not shown here in this diagram, but two lone pairs of electrons that forces these bonds to come down. And instead of having a 180-degree linear molecule, you actually have a 104.45 degree compound. Okay, so that's the general structure. And I'm gonna dive deeper into the hydrogen bonds and what allows for this to happen. And this is due to water polarity or the polar molecules. So last lecture, I quickly mentioned electronegativity, and this is important for science majors that you at least remember the term electronegativity for when you get to chemistry, because it's a very important concept. But in its simplest form, electronegativity describes how shared electrons within a molecule, for example, water, spends more time associated with one atom than the other. In this case, the electrons are going to be closer to the oxygen atom than the hydrogen atom. And that's because oxygen is more electronegative or has a stronger pull on the electrons than the hydrogen atoms. So that's termed electronegativity, and that's what actually gives us this partial negative and partial positive charge. So just envision, if you have two electrons between the oxygen and the hydrogen, if the two electrons are closer to the oxygen and electrons are negatively charged, then that means that the oxygen is going to have more of a negative charge than the hydrogen, which gives us the partial positive and the partial negative and the partial positive between the two. So polarity within a molecule allows us to predict interactions between two different compounds. If water is introduced to a second polar, so polar because you have this pole, negative, positive. Um, so if water is introduced to a second polar structure like itself, the separation of charges promotes intermolecular interactions such as hydrogen bonding. So that explains why we have this hydrogen bonding. If you have a polar molecule where the oxygen is slightly negative and the hydrogen of a second molecule is slightly positive, the second molecule is going to rearrange itself so that way the positive side is closer to the negative side. And you have this interaction here, similar to two magnets. You put the north and south poles together, they interact. So this interaction is what we call hydrogen bonding. So I've been talking about hydrogen bonding for quite some time, and it's because it's actually really, really important. It's one of the most stable intermolecular molecules, and it's the property that gives water its unique fundamental. Okay, so if a molecule is attracted to water, we call that hydrophilic. So water-loving interactions. So any two polar compounds that interact with each other or another polar compound that interacts with water, we call that a hydrophilic interaction. So the simple way to remember this is when we talk about polarity, likes dissolve likes or likes like likes. So polar likes polar and non-polar likes non-polar. You can't mix the two, well, you can, but you don't have the proper interaction. And that's what we call hydrophobic. So hydrogen bonds are not readily formed with nonpolar substances such as oils and fats. This is why when you mix oil with water, you have that separation between the oil phase and the water phase. And that's because you have a nonpolar compound, oil, trying to mix with the polar compound, water. And I'll explain that here. So hydrophobic, water fearing, and it will not dissolve in water. This is a ball and stick model. So each ball representing an element and the sticks representing a bond. So we have covalent bonds. The black balls are carbons, the white balls are hydrogens, and the red balls are oxygens. Okay, so we'll talk about this in the next lecture, but carbon is a very fundamental element because it has four electrons that are in its outermost shell, and that allows for four bonds. And these four bonds gives it a non-polar, so no charge separation. So if you have this long carbon chain, each of these carbons being non-polar, even if you do have a slight polarity at the end, the non-polarness of the entire compound gives it its hydrophobic properties. So if you were to mix this acid, which is the main component of coconut acids or coconut oil. So this is coconut oil. And if you were to mix this with water, it won't really interact properly because this non-polar region, this non-polar domain, is not going to interact with the polarity of a water molecule. Okay, so that's what we call polar.